Alright, today we're talking about chapter 1, or review 1. Right? So before we begin, I do teach from a textbook. However, that's not strictly from a textbook. For instance, I mean, it is strictly from a textbook, but I'm not just going to be reading off the textbook. There will be a lot of computation done in this course. So whenever I just read this, don't think that I'm not going to be showing any computation there. That's number 1. Number 2, I like to show the textbook because, well, I got to tell you a story about my best and worst professor I ever had. Okay, so it was my chemistry professor, and they were so bad that I had to go home and actually open my textbook to learn chemistry. And from that moment on, I became a good student, a great student, right? Up until that point, I depended on my teacher professor to teach me everything they could in an hour, and then I'd come back the next day and learn for an hour. But that's not how learning is done. You need to teach yourself outside of the classroom in order to fully understand the material. And so that's why in this particular course, we will be going through the textbook. I find it easier, right? So let's go ahead and snip this for review 1 here. Right. So exponents, prime numbers, and LCM, least common multiples, right? So introduction to exponents, the whole numbers, right? So the whole numbers, right here, consist of the number 0 and the natural numbers, right? So let's talk about natural numbers real quick. Natural numbers are numbers that you see naturally, right? You see 1 tree, you see 6 trees. You don't see -4 trees, and you don't see 0 trees, right? Now there's a minute difference between I don't see a tree and I see 0 trees, right? And that's just the technicalities of it, right? But when we talk about whole numbers, we can include the number 0, right? Natural numbers are numbers you see naturally. Whole numbers are numbers that are the natural numbers, including 0. And real quickly, notice the notation there, the N and the W, right? They stand for certain things. They stand for natural numbers and they stand for whole numbers. They're just written a little funny, right? Next up, we need the 3 dots. They're called ellipses. That means that they go on forever. And of course, we know this, right? We know the numbers go on forever. Right? Now let's talk about the operation of addition. So the operation of addition, we know, are numbers that are separated by the addition sign, or up here. Let me see right here. And we know that we can add. Well, we can add an infinite amount of numbers to one another if we wanted to, right? The operation of multiplication. The operation of multiplication is a little different because if you read here, it reads the operation of multiplication with whole numbers can be indicated by writing the numbers horizontally separated by a raised dot, separated by an X, or putting in parentheses. So there are 3 different ways to denote multiplication, right? Here's the dot. Okay, you should be familiar with that. Here's the times symbol, right? Times 6 times 8. And then, of course, if you just have something in parentheses, then that also denotes multiplication. Okay. We know that that repeated addition of the same number is shortened by using multiplication. So, for instance, this reads, or this is rather, 3 plus 3 plus 3 plus 3. Okay. Well, there are 4 3's, right? And that's the same thing, saying 4 times 3. That's where we get 12, right? Same thing here. There are 1, 2, 3, 4, 5 10s, and we multiply 5 times 10 to get 50. Okay. In a similar manner, repeated multiplication by the same number can be shortened by using exponents. For example, if 3 is used as a factor 5 times, we can write the following. So, kind of like how we did addition, right? We did 5 3's, and that's 5 times 3. Well, with exponents, we can say, if we said 3 times 3 times 3 times 3 times 3, well, there are 5 3's. We're multiplying 5 3's, so we can say 3 raised to the 5th power. Okay, and that's exponents. Right. So when looking at 3 raised to the 5th power, which is equal to 243, 3 is called the base, right? So let's put this off to the side here. We have a 3 and a 5. Okay, the 3, that's called the base, which makes sense, right? Because, I mean, you think about it, you can kind of think of like the 5 hanging off the 3 there, right? We call the 3 the base, and 5 the exponent. Okay. And up here, and 243 is the product, because obviously if we multiply numbers together, we get what's called a product, right? Make sure we're still recording, okay. The expression 3 raised to the 5th power is an exponential expression. All right, next up we're going to talk about variables. Okay, now this is a hotly contested debate. All right, let's just read it real quick. A variable is a symbol, generally a letter of the alphabet, that is used to represent an unknown number or any one of several numbers. Okay, so I've heard, people say, yeah, I was good at math if I put numbers in, and I mean, I guess they're not wrong, but it's kind of it's kind of a quip to just say, it's kind of stupid having letters in mathematics. Well, here's the thing. If I said 3 plus x is equal to 15, right? That, oh gosh, we have letters. That's horrible, okay? But the thing is, we use the letters instead of using, something like a question mark, right? Because, I mean, that's all the letters mean. The letters represent an unknown, right? We could say 3 plus question mark is equal to 15, but, I mean, we would quickly run out of symbols because it's a question mark, right? So instead, we just use some sort of letter, X, A, B, C. It doesn't really matter. We can even go crazy with some Greek letters, right? Alpha. But my point is, yes, we use letters in mathematics, but we use them because it's better than using question marks nonstop. Right. So start looking down here. It says the letters N and A are used as variables in the following discussion of exponents. So looking at this definition here, a whole number N is an exponent if it is used to tell how many times another whole number A is used as a factor. The repeated factor A is called the base of the exponent. Symbolically, when we have, we see A times A times A, dot dot dot, A times A times A, right? There are n amount of A's. Okay? Again, n just means some number, right? We don't know. But what you would do is if you have an n amount of A's, you would put that n right here in the exponent. Okay? And that's it. So the expressions with exponents 2, the base, down here. In expressions with exponent 2, the base is said to be squared. In expressions with exponent 3, the base is said to be cubed. With other powers, the base is said to be to the blank power. So we know, well, we should, maybe, right? If we have a 3 raised to 2, we know that's a squared, right? That 2 means squared. And if we put a 3 up here, that means cubed. And what is being said is, if we say 18, well, that's not a good 18, but you get my point. Then we say 3 to the 18th power. Okay. Excuse me. All right, now we get to some examples. Except I'm not really doing anything with these examples, so we'll just talk about them. Okay. So example 1, writing expressions using exponents. So in order to illustrate exponential notation, we show several products written with repeated multiplication and the equivalent exponential expression. Okay. So start from the top here. We have we have 7.7. We know 7.7 means 7 times 7. We know 7 times 7 is equal to 49. We also know we can represent that as an exponent. Okay, there are 2 7s, so we could say 7 raised to the 2nd power is equal to 49. Same thing can be said for 3, for B. Now C, a little different. I mean, just a tad different, right? Because we're no longer squaring, we are cubing. But we see 2 times 2 times 2. Well, there are 3 2's, and so we can put a 3. We can put a 3 for my exponent, and then that represents the exact same thing. 2 times 2 times 2 is the same thing as saying 2 cubed, or 2 raised to the 3rd power. And this 10 down here, we have 10 times 10 times 10 times 10. Okay, there are 4 10s, so we could raise 10 to the 4th power. Right. Example 2 reads, evaluate each exponential expression. So A, 6 raised to the 3rd, B is 5 raised to the 2nd, and C is 2 raised to the 6th. Well, okay, 6 raised to the 3rd power, that's just simply going to be 6 times 6 times 6, which is equal to 216. And B, being 5 squared, is 5 times 5 is equal to 25. And then c being 2 raised to the 6th power is 2 times 2 times 2 times 2 times 2 times 2 is equal to 64. Okay, so that is how we evaluate exponential expressions. Okay, next up we have prime numbers and composite numbers. Alrighty, so we need to define what a prime number is and what a composite number is. Right, so every counting number or natural number except the number 1 has at least 2 factors as illustrated in the following list. Okay, so every number except the number 1 has at least 2 factors. What does that mean? It means it has at least 2 numbers when you multiply them together will equal that number. Okay, so for instance 5, well I can get 5 from 1 times 5. 6, I can get 6 from 1 times 2 times 3 times 6. Okay, so again, notice how every one of these have at least 2. Okay, the only number that does not have at least 2 is the number 1 because, well, it's just 1 times 1. Alrighty. By the way, it says natural number, right? And if you recall, 0 is not part of the natural numbers, so obviously, 0, we don't call it prime or composite. Excuse me. Anyways, so check it out. All these have at least 2 numbers that equal that number, right? So for instance, let's look at 33, right? It's 1 times 3 times 11 times 33. All of these, well, I won't say all of them. Okay, so like 3 times 11 is equal to 33, and 1 times 33 is equal to 33, right? And I guess I kind of jumped ahead of myself up here when I said 6. But 2 times 3 is 6, and 6 times 1 is 6. All right, these are just factors of 6. These are numbers that can be represented by 6. Not that 1 times 2 times 3 times 6 is equal to 6. I jumped ahead of myself. I might have misspoken there a little bit. I'm sorry. Okay. Anyways, coming down here, notice that in this list, every number has at least 2 factors. But 5, 19, and 23 have exactly 2 factors. Okay, so check it out. 5, 19, and 23. They're highlighted in yellow. They have only 2 factors. Right? Such numbers are called prime numbers. The other numbers on the list are called composite numbers. So what does this tell us? Well, let's scroll on down. This tells us that a prime number is a counting number greater than 1 that has exactly 2 different factors, namely itself and 1. Okay, so a prime number that only has factors of 1 and itself. That's it. Composite numbers are numbers that basically are not prime numbers, right? Numbers that can be derived by factors that are numbers that are more than itself and 1. Okay, look at the attention here. 1 is equal to 1 times 1, and 1 has the only factor of 1. Does not have exactly 2 different factors, and does not have more than 2 different factors. Okay, thus 1 is neither prime nor composite number. Okay, it's important to know. Right. So example 3, another example we're just going to hand wave through because there's no computation here. It's just kind of showing you an example here. So the following numbers are prime because each has exactly 2 different factors, 1 in itself. Okay, so 2 has exactly 2 factors, 1 and 2. 3, 11, and 29, they're all prime because there's no other number when you multiply it by something else will get you to, for example, 29, right? No whole number. 2 times nothing will get you 29, 3 times nothing will get you 29, 4 times nothing, and so on and so forth. The only ones that work are 1 and 29. Okay. Determining composite numbers. Okay, so this reads, the following numbers are composite, right? So 1, 3, 5, and 15 are all factors of 15. Okay, so what this means is 15 times 1 will get you 15, but so will 3 times 5. 1, 3, 13, and 39 are factors of 39. What this means is 39 times 1 and 3 times 13, they're both equal to 39. Okay. 1, 7, and 49 are factors of 49. So this looks a little tricky, right? Because obviously 1 times 49 is equal to 49. But 7 times what is equal to 49? Well, 7 times 7. Okay. And then, of course, 51 kind of follows the exact same way. All right, so even and odd whole numbers. All right, so if a whole number is divisible by 2, then we call it even. If a whole number is not divisible by 2, then it is odd. It's pretty easy. Okay. Next up, we're going to talk about prime factorization of composite numbers. So now we're going to be getting to, I'm pretty sure, yeah, now we're going to be getting to where I do actually do some computation on the blackboard. So here, using basic knowledge of multiplication and division, we can find factors of relatively small counting numbers. For example, basic multiplication facts give 63 is equal to 9 times 7. Easy. However, for use in dealing with fractions, we need to find factorizations of 63 in which all the factors are prime numbers. So we need to factor 9. We can write 9 as 3 times 3. Okay, so 3 times 3 we see is indeed equal to 9. Okay, so this last product contains all prime factors and is called a prime factorization. Okay, maybe did I? Okay, I didn't necessarily touch. Yeah, we did. Never mind. I'm sorry. Prime numbers again are numbers that are the only factors are itself and 1. Okay. So let's see here. Going down here, regardless of the method used to find the prime factorization, there's only one prime factorization for any composite number. Okay. So what that means is for any number, it will only have one set of prime factorizations. Okay, and we'll see what that means here in a moment. Okay, so to find the prime factorization of a number, we need to factor the composite number into any two factors, and then we factor each factor that is not prime into 2 more factors, and then we continue this process until all factors are prime. Okay, the prime factorization is the product of all prime numbers. Okay, so we're starting to get into well. Okay, we will start here in examples. Okay, all right. Let's actually give it its own page. Normally I upload these notes, but like I said, these review sections are indeed review sections, and so there's not going to be too many notes associated with it because I am just reading it. Okay. But anyways, so we're going to have it reads, find the prime factorization of 90. Okay, so the way I do this is, the way I do it, and the way you probably should too, is whenever I do prime factorization, I start with my number, and of course you've seen this. You make a little tree, right? Okay, so I make this little tree, and so what I'm going to do here is, okay, so I've got the number 90. Okay, I immediately start with 2. 2 is just always easy peasy. So 2, okay, well 2 times what? Well 2 times 45. Let's fix that 4. 2 times 45. And then what I'm going to do is I'm going to box in the prime number so I know that I can stop there. So now I'm just going to continue to branch down the right side. Okay, so 45, well 45, that's, same thing as 9 times 5, right? So I put a 9 here and a 5 here. And I'm going to box the 5 because I know 5 is prime. Okay, well 9 is, and y'all can't see this toolbar here, but there's a toolbar in my way. See if I can move it out of the way. Okay, that helped a little bit. Alrighty, so 9 is 3 times 3, and I'm going to box those in as well. Okay, so I finally have all these that are boxed in, and they're all prime. Okay, so all these numbers are the prime factorization of 90. So my prime factorizations of 90 are 2 times 3 times 3 times 5, or in other words, 2 times 3 squared times 5. Okay, so earlier I said every number only has one set of prime factorizations, and that's what I mean by that. Every number can only have one of these sets. Okay, and which makes sense, right? Because 2 times 3 squared times 5 will only ever equal to 90. It won't equal anything else. So it's just kind of like a no duh kind of thing, right? But that is the prime factorization of 90. Okay, and then of course we see that down here. 2 times 3 squared times 5. Okay, so now we're going to find some prime factorizations of some other numbers. So let's get on that. These might get a little long, but we'll try this out. Okay, we're going to first start with 65. Okay. Okay, so again, I said I start with 2. Okay, I always start with 2. Well, 2 doesn't work here. Okay, 3 does not work here either. 4 doesn't, but 5 does. Okay, so 5 does work here. 5 is also prime, so let's go ahead and box that in. Well, 5 times what? Well, 5 times 13, and 13 also happens to be prime as well. So I can stop there. All right, so the prime factorization of 65 is just simply 5 times 13. Okay, I don't think I can fit 72 on here, so let's just go ahead and re-snip this and get a new one here. Okay, so 72, and put 72 up here. Okay, so let's start. 2 times 36, and I know 2 is prime, so I'm going to box that in. 36, I know 2 also works here, so I'm going to put a 2 here. And 18, okay. Well, 18, well, that's also, I can use 2 there as well. It's 2 times 9, right? And then we know that 9 is 3 times 3. And those 2 are prime. Okay, so what this tells me is 2, 1, 2, 3. Look at 2 times 2 times 2 times 3 times 3. Okay, and that's the last time I'm going to write it like that. Instead, what I'm going to do is I'm going to count them out. Okay, what I mean by that is notice how I wrote 2 times 2 times 2. Now, and for now on, I'm going to write just simply 2 cubed times 3 squared. Okay, because there are 3 2's and there are 2 3's. Right, and that's the prime factorization of 72. And 294, I am not looking forward to, but hopefully, or maybe, it's not as bad as I think. Alright. Excuse me. Alrighty, so 294. There are 2 different ways to go about doing this, and I will actually snip the other way. The other way being what they do, and actually let's get a smaller number, just to kind of get an idea. Okay, so example 5, we had 90, right? And what I did was I did 2 times 45, right? Well, you could just say, okay, well 90 is just simply 9 times 10, right? And you can go about doing that if you want to, and there's nothing wrong with it. So say 90 is 9 times 10. Did I say 2 times? I forget. 90 is 9 times 10, and then they prime factorization 90. Same thing with 90 here. We did 3 times 30. Okay, you could go about doing that, or the way I'm doing it, no big deal. But well, that's not what I meant. But in the end, you will still get to your solution. Okay. Okay. So 294. So 294. 294 is 2. Again, I always start with 2. So I mean, you can get your handy dandy calculator out, and I probably will after this one. So it's 2 times 147. Okay, I know 2 is prime. Okay, now 147. Okay, so I know 147 is not divisible by 2, so I can't use 2. So let's say 197 divided by 3. Okay, well 147 is indeed divisible by 3. It is 3 times 49. Now I know 3 is a prime number. Okay, and then lastly, I know 49 is the same thing as 7 times 7. So I can stop there. Okay, so what this tells me is that the prime factorizations are 2 times 3 times 7 squared, right? Because I've got 1 2, 1 3, and 2 7s. Okay, and that's 294. That wasn't nearly as bad as I thought it'd be. All right, so now we get to least common multiples. So we had to know how to do prime factorizations in order to get to the least common multiples. So the multiples of a number are the product of that number and the counting numbers. Thus, the first multiple of any counting number is the number itself, the number times 1. All other multiples are larger than that number. We are interested in finding common multiples and more particularly the least common multiple, LCM, for a set of counting numbers. For example, consider the list of multiples 8 and 12. Okay, so really quickly, let's jump back to what we're saying here. The least common multiple. Basically, the least common multiple, what it means is, what is the smallest number that both of these numbers will go into? Okay, well, if we count 8, 16, 24, 32, 40, 48, 56, so on and so forth, and 12, 24, 36, 48, 60, 72, and so forth, the smallest number that both of those will go into is 24. Thus, we have the least common multiple being 24. Right? So this means that the least, we'll come down here to the definition. The least common multiple, LCM, of two or more counting numbers is the smallest number that is multiple of each of these numbers. Okay. So again, what that just means is, well, I mean, I guess I've said it already, right? It's the smallest number that both numbers will go into. And let's, I'm pretty sure an example will really drive this point home. Okay. Okay. I will take this procedure along with me. Okay, so what I mean by I'll take the procedure with me is this textbook suggests, this is how you go about finding the least common multiple. Okay, so what that means is if you follow these steps, you'll find the least common multiple. Pretty easy stuff, but I mean, you have enough things to memorize, and you don't necessarily have to memorize the steps. And that's going to be a common theme in this particular course. There will be occasions where you go step by step, but it kind of gives you, it's just kind of like training wheels, right? Again, I mean, think about it. If I asked you to make me a peanut butter and jelly sandwich, you don't just in your head go, okay, step 1, step 2, step 3, step 4, right? You say, okay, so I know I need to do this, I know I need to do this, I know I need to do this, and then you make it. So that's kind of what I'm trying to get at there. And I probably just went in circles, so I don't know. I do that a lot. Anyways, so example 7 reads, find the least common multiple. Okay, so here's how we find the least common multiple of 3 numbers. We could, A, try to use our brains, okay? What is the smallest number all 3 are going to? Well, I mean, we have 8, 16, 24, 32, 40, 48. We have 10, 20, 30, 40, 50, 60. We have 30, 60, 90. So you could sit there and think of it, right? But instead, let's just do the prime factorization that we just got familiar with, okay? And I hope there's enough room here, but I mean, the numbers seem small enough, so we're going to try. So we're going to do 8 right here, okay? Well, 8 we know is 2 times 4. We can square that in, and 4 is 2 times 2. Okay, so the prime factorization of 8 is 2 cubed. Okay, so 2 cubed. All right, now 10. What are my prime factorizations of 10? Okay, well, 2 times 5. Oh, and that's it. That's easy stuff. Right, so the prime factorizations of 10 are 2 times 5. And then 30. Right, again, I always start with 2, so 2 times 15. If I'm able to, I always start with 2. I didn't mean to square 15. And then 15 is 3 times 5. And then both these can be squared, or boxed rather. So this means the prime factorizations of 30 are 2 times 3 times 3 times 5. Okay, so what I do is I did prime factorization on all of them. Okay, so what we're going to do now is we're going to look at these numbers. Okay, well, 8 uses a 2, and that's it, right? So it uses a 2. All right, now just bear with me here. And honestly, I like to keep green for the final answer, but we're just messed up, so whatever. So 8 uses a 2. Okay. 10 uses a 2 and a 5. Excuse me. A 2 and a 5. Well, 2 is I've already wrote 2 up here, right? So I'm just going to write a 5. right? And then 30 uses a 2, 3, and 5. Well, I've already written a 2 and a 5, so I'm going to write a 3 now. Okay, and now I'm just going to put them in ascending order, right? 2 times 3 times 5. Okay, now what I'm going to do, okay, so the first step I did was I did my prime factorization, and now I listed the prime numbers that are used in the prime factorization. For these three numbers, the numbers 2, 3, and 5 appear somewhere. Okay, for instance, or just to give an idea here, we know that 8 doesn't have a 5 or a 3, but that's okay. It has a 2, and we denoted it up here. The 10 just uses a 2 and a 5. It doesn't use a 3, but that's okay. And 30 uses all 3. Okay, so what we're going to do now is we're going to look at these numbers, and we're going to look for the highest power that you see. Okay, so the 2. What is the highest power of 2 you see? Okay, well, this is a cubed. This is a first power, nothing there, right? And this is the first power. So the highest power of 2 that I see is a 3. So I'm going to put a 3 up here. Okay. The 3, what's the highest power of 3 that I see? Well, I don't see a 3 here, I don't see a 3 here, but I see a 3 here, and it's raised to the first power, so it's going to stay 3 to the first power. And same thing with 5. I don't see a 5 here, I do see a 5 here, and I do see a 5 here, but both of them are raised to the first power. Okay, so the highest power 5 I see is also just 1. So what I'm going to do now is I'm just going to take the product of 2 cubed times 3 times 5, right? Well, 2 cubed is 8. 8 times 3 is 8, 16, 24. It's 24. And then 24 times 5 is 120. So 120 is my least common multiple of example 7, of these three numbers, 8, 10, and 30. Okay, and hopefully that helped you out. But that is how we do it. And of course, luckily, since I'm recording this, if you missed it, you can go back and watch it again. But that's how we find least common multiple. Right. All right. So this is useful. It could have come in handy a lot sooner, but like I said, you know how I said, when we did the 90 or any of them, I said I always start at 2, right? Well, this is a handy dandy, kind of handy dandy procedure to test for divisibility. What that means is, well, if the number a number is divisible by 2 if the unit's digit is 0, 2, 4, 6, right? Because obviously we know that I didn't divide odd numbers by 2, right? The 45 I didn't divide by 2. We can divide by 3 if the sum of the digits we can divide by 3 if the sum of the digits is divisible by 3, and then so forth with all these. Okay. I'll be honest with you, I don't operate by that test, but some among you might. So there it is. But anyways, I believe that does conclude. When we get to the test problems, yeah, that does conclude today's lecture of R1.